Today's video is about finding equations for exponential functions. I have here two functions expressed in tables. One of these could be written as an exponential function. Before we try writing the equation, I want to help you see how to recognize an exponential function. Looking at the function on the left, we see that we have an increase in x by 1 between each point, right? As x increases by 1, it looks like our y values are increasing by exactly 3. If we contrast this with the second function over here, as our x values increase by 1, what do you think is happening to these y values? It looks to me like they're getting multiplied by 3, and they're getting tripled. So in comparing these two types of growth, clearly I think because of that multiplication by 3, the second table is growing faster. The table on the left has a constant increase of 3 units as x increases by 1 unit. And if that increase continues and is constant in that way, that's a linear equation, right? Y equals mx plus b. Increasing by 3 in the y direction for every 1 in the x direction tells us that our slope is 3. And I can see by my first point 0, 6 that my value of b is 6. This first table has an equation y equals 3x plus 6. Our second table is the exponential function. In an exponential function, remember it's written as y equals a b to the x, and our value of b, our base, is the number that we multiply by an additional factor each time, and so here we're multiplying by 3 each time. A is the y value of our y-intercept, so I'm going to write the equation y equals 2 times 3 to the x. So distinguishing between linear functions and exponential functions, as x increases by 1, if it's linear, our y values will increase by a constant amount. We'll add something constant each time. And if it is an exponential function, we'll multiply by another factor of the base as x increases by 1. So let's write a possible equation for this function. Let's figure out if it could be linear or if it could be exponential. Maybe it's neither. As x increases by 1 in our first column, well, we go from 5 to 10, then 10 to 20, then 20 to 40. I don't see a constant sum happening here. It looks like these y values are doubling each time. So I'm going to write this in the form ab to the x. It looks exponential. Our a is our starting value. Our base is the number that we multiply by each time, 2. Let's take a look at this one. Our x values again are increasing by 1, and as x increases by 1, we go from 3 to 6. Here, we increase by 3 again, right? It doesn't continue to double. It continues to increase by 3 each time. That makes my slope 3 over 1, and we can write this as a linear function, y equals 3x plus, well, the y value of our y-intercept in this case is also a 3. In this case, again, I have my x values increasing by 1. Let's see what happens to our y values. Could be decreasing by 48. That's also cutting in half. And in fact, as I look at these numbers here, yeah, it looks like these are just divided by 2, or we could say multiplied by 1/2. So this is an exponentially decreasing function. We'll have a base between 0 and 1, which gives us that decrease. Our value of a is 96, and our base is 1/2. 96 times 1/2 to the x. Okay, so far, looking at a table where our x values increase by 1, it looks like we can figure out the difference between a linear function and an exponential function by looking at how those outputs increase or decrease. But what if we don't have an entire table? Are just a couple of points enough to write an equation? And we certainly know that's true for linear functions. If we have 2 points, we can write a linear equation between those 2 points. How about if we have 2 points and we want to write an exponential equation? Is that enough? Let's try this. Find an equation for the exponential function passing through 0, 5, and 2, 45. It looks like this is an exponentially increasing function because at 0 our output is 5 and at 2 our output is greater, 45. So it should have a base greater than 1 if we write it as an exponential function. One thing that's nice here is we're given our y-intercept, and so that tells me that in the form y equals ab to the x, my a value is 5. So I can start with this. Is one more point enough information to figure out what b is? I think so. This is some point xy that has to make this equation true. If we plug it in, I think we can solve for b. When y is 45, x is 2. This equation has to be true, so it should give us that value of b. If I solve this by dividing by 5, and let's see here, I need to take a square root to undo that square, or a 1/2 power, right? That's the same as a square root. We know that 9 technically has a positive and a negative square root, right? 3 and -3 would be solutions to this equation. They're both numbers whose square gives us 9. I can write that as plus or minus 3. However, when we're looking for an equation in the form y equals ab to the x, we know that our b value has to be positive, right? So I'm going to choose the positive b value. We're going to let b be a positive 3. So I'm going to put this together. Our a is 5, our b is 3. Here's our exponential equation. We can check this if we plug 0 in for x. 3 to the 0 is 1, and 1 times 5 would give me this first point, 0, 5. And if we plug 2 in, that's going to be 5 times 3 squared. 3 squared is 9, so 5 times 9 gives me 45. This is indeed an exponential function through those 2 points. Let's try this again. Find an equation for the exponential function passing through 0, 7, and 6, 273. I'm expecting another positive value of b because our function is increasing. From 0 to 6, we go from 7 to 273. In this case, round the value of b to 2 decimal places. We want to write an equation in the form y equals ab to the x. And having this y-intercept, we know that our value of a is 7. So let's start with y equals 7b to the x. I've got another point here that should satisfy the equation as an ordered pair xy, and that's going to allow me to solve for b. So in this case, when y is 273 and x is 6, we get a true equation. This time I'm going to solve this equation. I'm going to divide by 7. 273 divided by 7 is actually 39. I could certainly leave it as a fraction if it doesn't divide evenly. And now I want to take a 6th root on both sides, or in our rational exponent notation, I could take this to a 1/6 power. I do get actually 2 answers here. There are 2 values whose 6th power would give me 39, a positive and a negative value, because I have that 6th even root. But I'm just going to take the positive value of 39 to the 1/6 power because I know I want b to be positive. Let's get a decimal approximation of 39 to the 1/6 power. To 2 decimal places, it rounds to 1.84. So our equation looks like y equals 7 times 1.84 to the power of x. They asked us for a decimal for the base. You could also write the equation as y equals 7 times 39 to the 1/6 to the power of x as an exact value. Find an equation for the exponential function passing through 2, 5, and 6, 77. I'm noticing a difference right away with this one. We don't have a y-intercept, do we? So we don't have a value for a. What I do have is a ordered pair xy that should satisfy the equation and a second ordered pair xy that should satisfy the equation. If I take a look at what I get when I plug in the 0.25, 5 equals a times b squared. And let's also look at what I get when I plug in the 0.677. 77 is ab to the 6th. What I have is really a system of two equations in two unknowns. And we've worked a lot on solving systems of linear equations. Maybe we can use some of those same methods to solve this system of equations, even if they aren't linear. Two equations and two unknowns should be sufficient to find a and b. Let's try a substitution here. I'm going to solve my first equation for a by dividing both sides by b squared. And I'm going to plug that into my second equation. That gives me 77 equals 5 over b squared times b to the 6th. Maybe I'll write that as b to the 6 over 1. Because when I do that, I can see I have some common factors of b here. In fact, I could use my exponent rule that when I'm dividing numbers with the same base, I subtract exponents. That'll leave me with 5b to the 6 minus 2 power, or 5b to the 4th. Now I can finish solving this equation for b. Taking a fourth root to the 1/4 power and choosing the positive solution. I've got b as 77/5 to the 1/4. Let's approximate that to two decimal places. It's 1.98 or 1 98 hundredths. I've got my value of b. I also need my value of a, so let me go back here and plug in b and figure out that a is 5 over b squared, which is about 1.28. This gives me an equation y is 1.28 times 1.98 to the power of x. This equation approximates the exponential curve that passes through 2, 5, and 6, 77. I think we should try that one more time. Let's find an equation for the exponential function passing through 447 and 9, 6. This is an exponentially decreasing function, right? So we're going to expect that our value of b is a positive number between 0 and 1. Again, I don't have my a value or my y-intercept, but I can plug each of these in as a solution xy to the equation y equals ab to the x and come up with a system of equations. Plugging in 447, I've got 47 equals ab to the 4th, and my other equation would be 6 equals ab to the 9th. I'm going to solve either of these for a. I prefer to do the one with the lower power. The algebra is a little bit easier. So let's solve this first equation for a by dividing both sides by b to the 4th and plugging that into my second equation. Using my exponent rules, b to the 9th over b to the 4th, I'm left with b to the 5th. Divide by 47, and then a 1/5 power. I don't get two solutions this time because I have an odd power, but I'm going to calculate my b value to be 6 over 47 to the 1/5 is about 0.6. I'm going to do a few more decimal places. 6625. I'll take 4 decimal places. I'm doing that since this number is between 0 and 1. I don't want to lose too much information. If this is my value of b, I can plug it back in over here to find my value of a. My value of a should be 47 over that value to the 4th power, which is about, I'm going to calculate leaving my exact value in my calculator to be a little more accurate, 243.92. Here's my equation, 243.92 times about 0.6625 to the power x.